Hello and welcome to segment 2. In this week's segment 2, we will talk about optimizing input pipelines with tf.data. What are the bottlenecks in the data pipeline? Obviously, data pipeline in PyTorch you have seen exactly pre-process, load, right? Different way of invoking different number of workers, which will expedite the data process pipeline. Here in TensorFlow similar pipeline we will see, we will use tf.data API here, okay. We will see how to add the different transformations in that pipeline also, because be it image classification, be it your text processing NLP tasks, be it simple linear regression over any raw data from CSV, for everywhere you need to apply transformations, right? So transformation is one such integral part of data pipeline, how to include that, and different optimization techniques. Why input pipeline matters? Obviously GPUs process thousands of images per second, but can we give that thousands images per second to those processors, streaming multiprocessors? That is exactly the question that we are trying to achieve the answers for in each framework. PyTorch framework, we have seen how to give the optimization or achieve whatever we are trying to achieve to maximize the speed of data flow between the processor and VRAM of your GPU, right? A slow input pipeline means you are actually reducing the resource usage, because GPUs will stay idle till the time it gets the data. And the pipeline usually is these steps, right? Load batch from disk, because I will have this raw data stored in the disk, and then I'll pre-process on the CPU, because CPUs are good for pre-processing, that also we have talked about. But then we have to transfer batch wise to the GPUs, because GPU will take batch wise. Now what transfer that we are doing? We are transferring over PCI, and PCI has a maximum bottleneck in terms of bandwidth, right? Now if I am sequentially executing each and every stage for each iteration of the training phase, we will lose, because this transfer will take time and GPU will do the forward or backward pass based on the data it has got. So GPU will be idle if it does not get data over this transfer as soon as possible, and there is a bottleneck here. And optimized way to do it is prefetching, right? So prefetching we have talked about in PyTorch, where CPU prepares batch 1 or 2 batches ahead, and then it will start the process where GPU does not need to wait for, because then it can overlap the pre-processing and GPU forward pass together, and that way it can parallelly read multiple threads loading for files concurrently and do the batch processing, and the complete pipeline will do the overlap execution of pre-processing of data and the GPU forward pass or backward pass. Okay, so let's go into the handout. We last segment we concluded with the gradient tape, okay, and here first let's see a simple training pipeline, because this pipeline will be using in the after the data pipeline, because data will be processed before. So in this case we are initializing xtrain and ytrain, which are in terms of constant, tf.constant. So in real training we will have data tf.data API, which will be loading the data, pre-processing the data here. So basically preparing the data here, and then we are defining the weights and biases, which are variable type. So you can see that clear distinction between the data which are used for training here, which are tf.constant, and the variable that are used for training, which are basically the parameters of the model, which are defined by tf.variable here. Then we have the optimizer, tf.optimizers. There are many optimizers. We talked about optimizers in the PyTorch class in great detail, where to use which optimizer, basically the thumb rule, and then the losses as an empty list. And you can see that each step it's creating this data range of 200, and this particular segment is tracking which are the functions that will be involved in the gradient computation. So here y prediction and the loss function, which is basically the mean squared error computation between the y pred, the output of the neural network, and actual y value, which is the actual level. Okay. So now this is the real function and the mean squared error function which are involved in my gradient computation. So that's why we have kept in the gradient tape, and then we have the grad computation, which is tape.gradient of loss for each parameter here, or with respect to each parameter here, and then optimizer.apply gradients. Then we are zipping all the gradients through this optimizer, and then the loss will be appended, because in each iteration what are the losses we are keeping track, so that we can print the decreasing or increasing loss values, and then we can use these values to plot it. As you are seeing, this is basic training loop, right? In this loop we have the use of the gradient tape and gradient method for the gradient computation. Now for this case we do not need multi-loss, so persistent is not used here. Now we will talk about the eager and graph execution. So when we created that loop of the training pipeline, what happened? Python interpreter was looking at each line and executing, right? So that is exactly the eager execution by default. So tf2.x will do eager execution by default, and operations will run immediately in Python like NumPy and other frameworks that you have seen. And in the graph mode, it will not be executed as Python. So it will see what exactly the function that is being defined under this decorator, and based on that we will actually build the graph, which will be a C++ graph which will execute that particular graph. So we usually use graph for the production and training inference, because development and debugging is easier in eager mode, as I said, and one such eager mode of execution that you have seen in this particular training pipeline or training loop. Now let's imagine here we are trying to do a heavy computation here that is defined under this function, which is heavy computation function. Now when I compile this graph, basically tf.function, so that means this will be compiled the graph version, and the data which will be let's say tf.random.normal distribution data that we have initialized here, that will be executed after that. Now here we are just measuring the time for the eager execution and for the time which is executed in the heavy graph, because here we have the heavy graph defined as a tf.function. So either keep that function under the tf.function decorator or apply tf.function API, both are same, right? So here heavy computation is being compiled as a graph, and in this case I am directly calling this heavy computation with the data here and measuring the time between these two. You can see here that we are getting, for this simple computation, we are getting almost 2 times speed up. So the eager execution took around 1.5 milliseconds and graph execution took almost around 0.8 milliseconds. And this is just a simple example, and you imagine that you are applying for your training pipeline, right? So that the first call will not take the time computation into account. That was the warm up trigger that happened here, just to trigger the warm up so that warm up time is not computed in this particular section where we are computing the time for the graph execution. So now you see the graph execution as tf.function decorator. Here you can see that the same forward function pass, which is the forward pass for the neural network or any AI algorithms. Here is a simple forward pass which has two layers. One is the ReLU and applied on the tf.matmul, which is the hidden layer, and then the reduce mean is applied on the logits of this particular layer, which is the previous layer, which is giving me scalar output, right? Now this particular function is defined under the hood of tf.function decorator. Now I have this function as a complete graph, and when I call this particular graph, I can execute as a graph execution in C++ in the backend. Now few things to note here. So this is just a graph template that is created while defining this function, right? I exactly do not know what are the values, dimensions, shapes of x, w, b will be, and to get a concrete function for this specific input signatures, we can actually define signatures using tf.tensorspec. And here you can see that we are defining the tensor spec for x, w and b here. Here we are taking any input, output is x shape, here batch is 4, 8 is the output shape, and here is the tensor of shape 8 as the output. So this is the bias. Okay, so now when I call this getConcrete function method over this particular specs, then the forward function pass or forward pass function, which was defined under the hood of tf.function decorator, which is essentially the graph, execution graph, which now has a specific specification template attached to it. And now I can get the graph, actual graph, which is graph equal to cf.graph, and if I just iterate over the operations of this graph, I can actually list down the operations, and you can see the operations here, starting from the x, w, b, which are the placeholders for which I have defined the specs through this concrete function, and then we are defining this, and you can see that graph inputs are these and graph outputs are basically these. Okay. So this is how we usually inspect the computation graph, okay, by get the concrete function for a specific input signature, and then defining exactly what are the operations that will be happening. Now with this, actually we can inspect the graph elements, and we can go for different execution of the forward pass, different way of execution, eager mode and the graph mode. Eager mode obviously we will use for the debugging, because if we do the graph way of execution, we will not be able to actually print exactly what is happening after each line. Okay. So now coming to the input pipeline, we can see that this naive execution of usual training workload is basically load the data, pre-process and then train. And then GPU idle is here, because now I have to do the loading again of the data and pre-process. So this particular segment of time, the GPU will be idle. And when we optimize this particular pipeline, we have the load plus pre-process. So load and pre-process, that will be happening before the training starts, right? But now you imagine that I have already prefetched few batches, right? And I can pre-process. And then when I start the training of this particular batch, and that point of time, actually when I am starting the pre-process, I can start loading, and when I am starting the training, I can actually pre-process. So basically you can see that this is called the pipeline, right? So the training is going on at the same time of loading and pre-process. And that way we are actually saving this GPU idle time here, and here by ideal, let's say, pipeline, we can get 0 idle time, okay, or 0 waiting time. So here this is a very naive way of defining the or creating the data set. So there are three methods in this particular API, which is the in-memory way of defining things. Like I have small data set which can be accommodated in the particular RAM size which I have. So np.random.n, which is, let's say, initializing this particular data, as type np dot, so numpy array is defined images, and the labels have been also defined as 0 to 10 with the values here. Okay, so now this ds.numpy is converting these images and labels slice by slice, that means each element wise, and using data.dataset dot from tensor slices. So I have already the numpy tensors, and from numpy tensor slices I am creating this data set. So from tensor slices I get the element specification as well. So now we can see that I have this complete array. Slices are actually loaded into this data set. So now this entire method is in memory, very fast, but this usually will be applicable for your data set which are very low in size, because in RAM I will not have space for accommodating, let's say, GBs of data, right? Method 2 is from Python generator, where I can, from a range of values I can generate, right? And tf.data.dataset from generator will take this let's say generator values and see the output signature here based on what shape I am defining this tensor as, and the data type as well. Okay, so that's how this is another way of defining this data set. And the third method is the directly applying range. Okay, so now obviously from generate data.dataset dot from generator method will actually use not the in memory way, but it will actually take the slices, or each based on the signature each element will be loaded, and then it will actually be stored into this data set which we will be using for my training. And the third method is basically when we want to generate synthetic data from range, basically we can directly use this dot range to, let's say, create the labels or create synthetic data set and so on and so forth. And you are seeing the first three samples from this ds.numpy, and we can actually pick the elements as we go from the ds.numpy.take. So it will take the elements, three samples, and we can actually print that. So this is one way of pick at different elements of the data that we have just formed. So now these are the widely used three methods, okay, for creating the code data set. And now we can apply different transformations or pre-process. So you can see that this pre-process function have been defined under this decorator. So basically this will be an optimized graph which will, let's say, take images and labels, and it will perform several line or series of transformations or pre-processing stage at one go. How? You can see that here we have the image to tensor casting, and then we are applying this the normalization, and then the clipping value is done to keep this value range between -1 to 1. Okay, so let's say these three functions or three methods that I need to perform while operating on the image dataset. So it will return image label per image that it will receive, and it will pre-process, and it will return the image plus label as the list here or tuple here. So now we can build the optimization pipeline. How? We can actually do the optimization as well. Now tf.data set from tensor slices is one method. We talked about that method, and now I have the images and labels, right, which is basically the processed data. Dot map will parallelly apply the pre-process on each slice based on the number of parallel calls that I am defining here, and that is the key optimization technique in the data pipeline or optimizing the data pipeline. So here the map method is applied on each slice that we are getting, and this pre-process will be applied on these images and labels based on how many number of workers that I have. So now we can contemplate the number of workers method in the PyTorch, and here AutoTune will actually see exactly what is the load in my processor as well as how many number of cores that are available in my target processor, and based on that it will automatically create the number of parallel calls which will be highly optimized for your particular parallel CPU workloads. And if I need to shuffle, if I need to batch or group into batches per sample and then prefetch, if I need to activate, again tf.data.autotune, which will see the number of cores and how many batches it needs to see. So next batch, while the GPU will train, it will prefetch the next batch or not. So now this DS, the data set which we have been creating by this dot map, dot shuffle, dot batch, dot prefetch. So basically these methods that are applied in this API, which will optimize at one go for this entire pipeline. And you can see these specs, element wise specs in this particular data set by iterating through this ds.element spec. Here you can see the spec. So basically the shape of the images batch wise, because I have 16 batches, right, and you can see the shape, output shape also. Okay, so batch to images, image value range also, and that is exactly the labels plus images and labels. So this is basically the shape of the tensor that we are creating here, and the value ranges, because we have applied the normalization and clipped the values between the given range of -1 to 1. That also we are seeing here how much maximum value it has clipped. Okay, so this is using tf.data API. We have defined the data set. Obviously now you can use from generators, from tensor slices, whatever method that you feel suited for your particular target RAM, we can actually apply that. Okay, so that way we can flexibly define this data pipeline, and at the same time we can apply further pre-processing also. Here we are seeing in this section the caching of element wise, because some pre-processing are redundant, because we are applying in each iteration the same pre-processing for each slice of data. So here let's see, if I am doing the map which is operating on each slice of data per batch, obviously, which runs every epoch. If we do not do explicit caching, it will not apply caching on the pre-process, let's say. That means it will apply the same routine calls every time it encounters the map method. And in this case the pre-process is basically a simple cast, let's imagine. And now we are defining this map which is operated on this data set, which has been created by dataset.range. Obviously again you can create the dataset by from slices, from generators, from range, and dot batch you can define with all the parameters that you have seen in dataset defining as well. For simplicity here, defining this map method, just focusing on map method here, and we are applying this pre-process. Now you imagine that for my each epoch I am calling this particular pre-processing, right? So I have this pre-processing where I'm trying to fetch data in each epoch, right? And calling that for ds no cache, because ds no cache has pre-process in it, right, without the cache call, and ds cache has pre-process init map with cache call, which will see in the first iteration what exactly pre-process method that I have applied. I do not need to call that particular method again, but I just need to transform that data which is coming for this particular slice. So this initiation will not be cached, so this entire map method is cached here. Without cache, I am taking around 16 millisecond in first data, second first iteration or first epoch, second iteration for second epoch I am taking 11.2 millisecond, third epoch, fourth epoch without cache. With cache, you are seeing we are first taking 22.8 millisecond. This is reasonable because first iteration will actually have no cache, the map method, so it will cache the map with pre-process whatever casting we are doing it here, and in the subsequent process it just transforms the data which is incoming, right? So it is taking almost 4 times less time, so 4 times speed up we are gaining for this particular simple cache method, using cache method for this pre-process. Now you imagine you have complex pre-processing pipeline, right? You have image flipping, image clipping, image normalization, image rotation, right? And you can map and cache the pre-processing stages, and basically you can reduce the pre-processing stage in the subsequent epochs, and that way we can actually reduce the data pipeline or data pipeline overhead subsequently. We can have parallel processing, pre-processing as well, because now we can actually do, obviously now we have this augment, let's say one method which is defined under tf.function. I will not go again detailing this xy initialization here, but in the sequential map we have tf.data.dataset from tensor slices, and .map method is computed using this augment and number of parallel calls equal to 1, because in the previous calls we did not have initialized any number of parallel calls. But if we apply this data.autotune here by number of parallel calls, obviously here number of batches are 32, same number of batches I am doing pre-processing for the sequential mapping and parallel mapping, and just measuring the time it is taking. And you can see for this simple parallel number of workers, for worker 1 it was taking 100 milliseconds, and with parallel map I am getting improved mapping with auto-tune, which is 1.28 times for this simple pre-processing. But if we have complex pre-processing, you can increase this speed up as well. So each time we are trying to see how to optimize or get the maximum acceleration through this particular optimizations. Another way of doing optimization is tf record. Why tf record? Because sequential reads of data from the storage, because we have to read the raw data from disk storage. It saturates the disk bandwidth, and no per file overhead like let's say JPEG or PNG file we are executing directory wise will not have this pre-file overhead. So basically naive way of doing things is basically writing tf record here and reading tf record here, right? And if let's say we are applying this prefetch, right, with tf.data.autotune, which we talked about, this will actually improve the performance also. And you can see the tf record pipeline has been verified or not. So the usage of tf record is demonstrated here. You can just go through, because it's similar to the dataset forming, then reading and writing the or reading the raw data using the tf record. Here we are using the images. You can replicate the same process for other data types also. Okay, so basically the recommended pipeline is source, then cache, then shuffle, then map with auto tune, and then batch, and then prefetch and TF record. So with all these optimizations, here is one such complete pipeline where we have the TF function defined over the augmentation function here, and the optimal data set is been defined here with this all auto tunes and caching as well as the prefetching, and here you are seeing the complete pipeline summary. So this way you can have very flexible data set pipeline formed for your training based on what type of target that you have and what type of data that we are using from the disk. Okay. So in the subsequent lectures, we will actually go or take a deep dive into the optimizations in the graph execution. Thank you for this segment.